Okay, today we will look at AIME 1998 and we will solve 5 easiest problems, as usual. So let's start from the first one. It's not difficult, but however, I saw many students make mistakes here. So for how many values of k, 12 to the power of 12 is the least common multiple of the positive integers 6 to the power of 6, 8 to the power of 8, and k. So let's write what we want to see. We want to see that 12 to the power of 12 is least common multiple of next numbers. 6 to the power of 6, 8 to the power of 8, and k. Well, of course, when we work with least common multiples, it always makes sense to look at prime representation of any number. So we need factorize each of these numbers and represent it as a product of primes in different powers. Well, if we speak about 12, it is 2 to the power of 2 times 3. And therefore, 12 to the power of 12 equals 2 to the power of 24 times 3 to the power of 12. About 6 to the power of 6, it is obviously 2 to the power of 6 times 3 to the power of 6. And 8 to the power of 8 equals 2 cubed to the 8th power. It's 2 to the power of 24. Well, and k is unknown for us. So let's write our problem in this way. So 2 to the power of 24 times 3 to the power of 12, which is this number, equals least common multiple of the next numbers. And the first one is 2 to the power of 6 times 3 to the power of 6. The next one is 2 to the power of 24. And the last one is k. So we want this number on the left side to be the smallest number that is divisible by each of these numbers. Let's notice it's a very important moment that 2 to the power of 24 is present here. So for this number, if we speak about least common multiple, in any case, because 2 to the power of 24 is present here, this 2 to the power of 24 has to be present here on the left side, because you have this large power of 2, and in order the number to be divisible by each of these numbers, it must have this 2 to the power of 24 in its prime decomposition. So this one is present. Next one, 3 to the power of 12. Okay, so let's look, for example, for k. What if k equals 3 to the power of, for example, 1? Obviously, in this case, you see that the maximum power of 3 that is present on the right side is 3 to the power of 6. And 3 to the power of 12 is redundant here. We don't need here to have such large power of 3. It will be enough to get 3 to the power of 6. We will have no problem. In this case, it will be divisible by this one, and this one. Even if k equals 3 to the power of 4, the maximum power of 3 that is present here on the right side is simply 6. And 12, again, is not necessary here. So in this case, it's enough for us to get here 3 to the power of 6 again, and this number will be divisible by each of these numbers. So in order here to have 3 to the power of 12, some of these numbers from the right side, it should have 3 to the power of 12 in its prime decomposition. So therefore, k must have 3 to the power of 12 in its prime decomposition, but it also can be multiplied by something else. And of course, what can be the other number here by which this one is multiplied? Of course, it should be a power of 2, because this one, it can be divisible only by the number that looks like 3 to the power of I times 2 to the power of j. It's like necessary representation for each of the numbers on the right side. If it's not how the number k looks, there will be no divisibility. So therefore, our conclusion that k should look like 3 to the power of 12 times 2 to the power of j. And now we have a very simple question. So what should be this power of j? Well, if we look at j equals 1, in this case everything works out. You will see that it is the least common multiple. If j equals 2, everything works out, and so on. And what is the maximum value of j? What is the maximum power of 2 allowed here? Obviously it's 24, because if j is larger than 24, there will be no divisibility. So the last one is 24. And very important thing, it looks like we have 24 different options for j, and it is like the final step where many students make mistakes. So you are asked how many different values of k work for you. And it looks like you should here tell the answer 24, because each value of j gives you different value of k, and it looks like you found 24 options. But the main trick here that you should also notice that j equals 0 works perfectly for you, really. If j equals 0, this one is 1, and k is 3 to the power of 12, and it also works, so this one will be the least common multiple. So it's very important not to skip 0, and these are possible values of this power j, and therefore we have 25 possible values of j, and therefore we have 25 possible values of k. So k looks like this. J goes from 0 up to 24, and k can so we have 25 possible variations, possible options for k. This is it. So it is the end of this problem. Let's go to the next one. Okay, let's go to the problem number 2. We need to find the number of ordered pairs xy of positive integers that satisfy these two inequalities. So if you have minimal experience with such problems, you know that it makes a lot of sense to draw x and y axis and to mark the region on the plane where you have all the necessary pairs, all the needed pairs xy. It's usually the best way to go, because if you try to solve it like directly, you can try, you will spend a lot of time and it doesn't look obvious how to find the number of pairs. But if you represent it in the way in terms of geometry, so you basically will draw the area on the plane where all the pairs xy belong. In this case, it will be much easier to solve. So when we want to work with the first one, it makes a lot of sense to separate it, because it is actually two different inequalities. And the first one looks like x less or equal than 2y, and the second one looks like 2y less or equal than 60. And therefore, here we have y is greater or equal than x over 2, and here we have y is less or equal than 30. This is it. So let's draw each of these inequalities basically on our plane. So in order to draw this one, we at first look at y equals x over 2, and it is obviously the line that passes through the origin, and we know that the angle of inclination of this line with respect to x-axis has tangent of 1 over 2. So tangent of alpha is 1 over 2, the angle between this line and the positive direction of x-axis. So, and where do we have all the points such that y is greater or equal than x over 2? Obviously, we speak about this area of the plane. So this half plane that is above this line works for us. So everything here. This line is included, by the way, because we have y is greater or equal, so the points xy that belong to this line, they also work for us, because equality is allowed. So, and finally, y is less or equal than 30. In this case, we draw a line, y equals to 30, and we need all the points with y coordinate less or equal than 30. It means that everything below this line will work for us, and the needed region that we are looking for is intersection of this half plane that is above this line and half plane that is below this black line. Therefore, it is the area that we are looking for. It is the area that we are looking for. It is restricted by this line and this line. The points on these two lines also work for us, and it is actually the region where every point xy works for us. So, and we need xy from this area. However, here we have a restriction that not all the pairs xy, but only of positive integers. However, every point or xy with positive integer coordinates from here will work for us. This is it. But of course, we have another inequality here. Let's work with this one. Another one we can also separate into two portions. So at first one, y less or equal than 2x, and the second one, 2x is less or equal than 60, which is equivalent to y is less or equal than 2x. We will leave it without changing. But here is x is less or equal than 30. In order to look at, for example, this one, x less or equal than 30, we draw the line, x equals 30. It looks like this. And we need everything on the left side of this line, because here on the left side we have x coordinates that are less than 30. And for this one, we draw the line y equals to x, y equals 2x, and again it is a line that passes through the origin, and we know that the angle of inclination for such line has a property that the tangent of this angle equals 2. So it means that for this angle, here we can mark it as beta, we know that tangent of beta equals 2, and we need y coordinate to be less than 2x. If we draw this line where it's like equal to x, we need y to be less. It means that everything below this line works for us, everything below this line. So therefore, our area that we are looking for is exactly the area between this line and this line. So the area between these two lines work for us. So from the first inequality, we got that everything between these two lines, this like infinite triangle, works for us, and here we have this infinite triangle works for us, and of course we need both of them be true. So the total area that we are looking for is this intersection, this quadrilateral that we are looking here. It's exactly what we need. So every point xy where x and y are natural numbers, if it belongs to this quadrilateral, that's the point that we need. And we need to calculate how many points xy with integer coordinates belong to this quadrilateral. So let's look closer. Basically, now you can look at these lines and you can notice that, of course, this figure here is not just a rectangle, but it's simply a square, because this is y equals 30, this is x equals 30, so the coordinate of this point is simply 30, 30. And the trick here is if you try to calculate manually how many integer points xy do you have in this quadrilateral, you can do it, but it will be pretty tedious process. It will be pretty long, so you can go like along these lines that are parallel to y-axis, and up to this point everything will be fine. But when you encounter this this area, so you will go like along these lines, it will be pretty difficult and not the best way to go. The best way to solve this problem is to look at the total number of points xy with natural coordinates in this square. And we also need like xy to be positive. So here in this square, you can quickly tell that you have 900. 30 times 30, it means that you have 900 points xy, where both x and y are natural numbers. And after that, you will throw away some number of points with the natural coordinates xy from this triangle, and the same number of points you will have in these triangles, with natural coordinates. And what will left is a number of points with natural coordinates xy in this quadrilateral. That's the main idea. Obviously, when you look at the number of points with natural coordinates xy in this triangle, it will be exactly the same as in this triangle. Why? Because this triangle is exactly equal to this one. Tangent beta equals 2. Tangent alpha equals 1 over 2. So these numbers are reciprocal, 2 and 1 over 2. When you have these two angles where tangents are reciprocal, for example, if tangent beta equals 1 over tangent alpha, it immediately means that for acute angles, alpha plus beta equals 90 degrees. It's a simple problem on trigonometry, you can check yourself, and therefore if the sum of these angles is 90 degrees, so beta equals 90 minus alpha, and therefore this remaining angle is also alpha. So we can get rid of beta here. I will just erase it. So because these two small triangles, they are pretty much the same, it means that they contain the same number of natural pairs xy, and therefore you need to count this amount only in one of these triangles, and then you will multiply it by 2, and you will subtract the result from 900, and you will get the number of natural pairs xy in this quadrilateral. And if you look at points with natural coordinates, like you will go along this line, you will go along this line, along this line. This line has coordinate x equals 30. The intersection with this line, which looks like y equals x over 2, it will be exactly 15. So 15 here works for you, but this is on the border of your quadrilateral, so you will not take this point because it belongs to quadrilateral, this point, so you need everything inside this triangle. And inside here you will have 14 points with the integer coordinates. Along this line you will also get 14 points. Here you will have 13, 13, 12, 12, and so on, and eventually 1, 1. So the sum of points with integer coordinates, the total number will be 14 plus 14 plus 13 plus 13. We are looking at the points xy that are exactly inside this triangle, right? The points that are on this line, on this hypotenuse, these are already the points that belong to this quadrilateral. They work for us. So we are looking everything that is inside our triangle, and eventually it turns out to be the sum 1 plus 1 plus 1. So it is basically the doubled sum of arithmetic sequence that looks like 1 plus 2 and so on plus 14, and this sum should be multiplied by 2. If you calculate this sum, usually the formula is the first one plus the last one times how many numbers you have divided by 2. It is the sum of this one, and times 2. So therefore 2 cancels out, and this value is 14 times 15. What is this one? So 14 times 15. 14 times 14 is 196, and plus 14, and the result will be 210. 210 is the number of points x, y with natural coordinates xy that are inside this triangle. So therefore 210 is here, therefore 210 is here. The total number in the square of such points is 900, and therefore what is left for this quadrilateral is 900 minus 210, which will be exactly 480. And it is the right answer for this problem. 480 is the number of natural pairs xy that satisfy these equations. 480 is our answer. This is it. So let's go to the next problem. Okay, we are going to the number 3. We have a graph that partitions the plane into several regions. We need to find the region that is bounded by the graph, and we need to find the area of such a region. Again, we will use a coordinate plane to solve this one. And when you have a graph that looks like this, obviously you notice that we have absolute value of x here, and in order for us to work normally with it, we should tell that absolute value of x is simply x when x is greater or equal than 0, and absolute value of x is simply minus x when x is less than 0. In this case, we will represent this equation we will separate it in two different scenarios. The first scenario, when we have a non-negative value of x, in this case it looks like y squared plus 2xy plus 40x equals 400. At the moment, it's not obvious at all how to draw such graph, but however, you see here that it looks like almost a complete square, y plus x. And let's try to get it. Y plus x squared minus x squared. Really, if you get this one minus x squared, you will get exactly this expression, plus 40x equals 400. Now you bring everything, take everything like this and bring it to the right side, and everything will look like y plus x squared equals x squared minus 40x plus 400. And here you recognize that you have a complete square on the right side, which is x minus 20 squared, and it is equal to y plus x squared. And now everything looks super simple, because you have the condition that the squares of two values, that they are equal. It's similar to the case where a squared equals b squared. Therefore, a must be equal b, or a must be equal minus b. Two of these options work for you. So let's, for example, work with the first scenario. Y plus x equals x minus 20. And also the second scenario, we will mark it that y plus x equals 20 minus x. And remember, very important thing, we work here with an assumption that x is greater or equal than 0. X is greater or equal than 0, and so let's look, for example, at the first scenario. And also, we don't forget about assumption that x is greater or equal than 0. It is the first thing. So it is obviously the equation of a line, and it is the line that looks like y equals minus 20, and again, with condition that x is not negative. Let's draw it. So we draw a coordinate plane right away here, and y equals minus 20. So it will look like this, the line that parallel to x-axis, it passes through the point with coordinate minus 20 on y-axis, and x is greater or equal than 0 is everywhere here. So we consider only this portion of this line. Just a second, only this portion of this line that is on the right side. That is the portion that we need. This one is not allowed because it is significant requirement. Okay, so here the next situation, y plus x equals 20 minus x. It is also the line with equation y equals minus 2x plus 20. What can you tell about this line? Well, obviously it has like this tangent of inclination with respect to x-axis, which is equal to minus 2. And let's substitute here, for example, x equals 0. When x equals 0, y equals 20. So this line passes through this point with coordinate 20. And when x equals, for example, 10, y equals 0. In this case, it passes through the point with coordinate 10 on the x-axis, and so we can draw the line right away. So it will look like this. Passes through two of these points. Let me be a little bit more precise to make sure that it really passes. Okay, so now it's done, and this is it. So we will just continue, and we know about this line that the tangent of the angle between the line and the positive direction of x-axis, it is the tangent of this angle, alpha, equals minus 2. So tangent alpha equals minus 2. Alpha is obtuse angle, and everything works out here perfectly. So that's how it should be. Okay, so what is the area that we need? What is the region? We shouldn't forget here that x is greater or equal than 0, so we need everything on the right side here, like on the right side of y-axis. Therefore, we need only this portion of this line. So let's mark it. We need only this portion of this line that is here, and it would be great also to mark the point of intersection of these two lines. And it's not difficult to find. This line intersects with this line. How to find the coordinates of such point? Well, we will equate here. So let's do it. Minus 20 equals minus 2x plus 20, and therefore 2x equals 40 and x equals 20. So therefore x equals 20. And what about y coordinate? Well, maybe we will not need it, but let's get it. Y will be equal to minus 20. Y equals to minus 20. So this point of intersection has coordinate 20 with x and minus 20 with y. This is it. So here we have this line, this portion, and we found the point of intersection. Let's work separately with the next case. The next case is where we work with absolute value of x equals minus x. We substitute it here, and the equation will look like this. So let me draw it here. Y squared plus 2xy minus 40x equals 400. And after here you again separate the perfect square, it will be y plus x squared, y plus x squared. Here you will have minus x squared minus 40x equals 400. And after that, when you bring this expression to the right side, it will turn out to be y plus x squared equals x plus 20 squared. And again, don't forget that we are looking at the scenario where x is less than 0. So here we have two possible options. The first option looks like this: y plus x equals x plus 20. And another option is y plus x equals minus x minus 20. And because x is less than 0, again, we consider two scenarios. This scenario with condition that x is less than 0, and this scenario again with condition that x is less than 0. So this one is simply the line y equals 20. So let's draw the line y equals 20 here. And again, so we don't need this portion of the line because we are only interested at values of x that are negative, that are here. So we need only this portion of the line. And with this one, let's look at this equation, y equals minus 2x minus 20. So when x equals 0, y equals minus 20. So it passes through the point 0 minus 20. So this line passes through this point. And also another point, for example, when x equals minus 10, y equals to 0. It means that we can mark here the point with coordinate minus 10 on x, and this line passes through these 2 points. And again, we need only this portion of this line that is on the left side, because we are looking only at the option where we have only negative values of x. So we don't need to extend it here, because here in this half plane we have positive values of x and we need negative values of x, so only this portion of the line works for us. And again, we need to find the point of intersection of these two lines, which will be pretty simple, as I think, because the first line for you is provided with an equation y equals 20, and this one is with y equals minus 2x minus 20. When you equate, you will have the equation 20 equals minus 2x minus 20, and if you solve it for x, it will be x equals minus 20. So the coordinate of this point in terms of x is minus 20. Let me write it here, minus 20, and the value of y is on this line is 20. So we are looking at the region bounded by this graph. At this moment, it's obviously that we are looking at this region. So let's look at this one. What is it? What is this figure? It's obviously a parallelogram, because this line is parallel to this one is parallel to this one. You can look at the tangent of inclination of this line, and you will get that it also minus 2. So the tangent of this angle, let's look at beta. The tangent of beta is also minus 2, the tangent of alpha minus 2. So these two lines are parallel, and you need to find the area of this parallelogram. And it's very easy to do. You have to look at this figure and notice that it consists of two equal right triangles. So, and it is a right triangle. What is the length of this leg? It goes from x equals 0 here to x equals 20 here, therefore this is 20. And what is the length of this line? It's on y-axis from minus 20 to 20, and therefore the total length here equals 40. And this tangent alpha, it's minus 2, so therefore this tangent of this angle, for example tangent gamma, equals simply 2, because they both add up to 180, so their tangents are opposite. And we know that the tangent of this one is also, tangent gamma is also 2. By the way, it's even redundant, because what is the tangent gamma? It's this one divided by this one. Yeah, exactly, it is 2. It just gives us additional proof that everything is correct with our solution. And in order to find the area of the parallelogram, you just add the area of this triangle, which is 40 times 20 over 2 plus the area of exactly the same triangle on the left side, 40 times 20 over 2, which is simply 40 times 20, which is exactly 800. So 800 is the total area of this parallelogram, and it is the area of the region that is bounded by this graph. So this is it. This problem is considered to be fully solved, and we are going to the next one. Okay, the next one that we will solve is geometry number 6. Again, a short and simple problem on geometry. So you have a parallelogram, ABCD, and let's draw it right away. So we have a parallelogram like this, and we mark the vertices. So A, B, C, D, and extend DA through A to a point P. So DA is extended through A to some point P. So we make it. So we extend it to some point P here, and let PC, so therefore we need to connect P and C, and it meets AB. It meets AB at some point Q here, and it also, this line PC, it meets DB at the point R. DB at the point R. So let's draw the line DB and mark the point R here. So And after that, we are told that PQ is 735. So this segment is 735. QR is 112. So this one is 112. And you need to find RC. So very short problem. In general, when you work with parallelograms and when you extend such lines, like this one, you obviously should understand right away that you will get a lot of similar triangles. For example, what similar triangles do you see here in the picture? Well, immediately this triangle is similar to this one because this line is parallel to this line. Or, for example, this triangle is similar to this triangle because this line is parallel to this line. Or, for example, this triangle, this big triangle, is similar to this triangle because this line is parallel to this line. Or this triangle is similar to this triangle because this one is parallel to this one. As you can see, I found like 4 different pairs of similar triangles right away. And obviously, it will be the key to solve such problems because these segments are actually sides of these similar triangles. 112 is this side of the triangle, which is similar to this one. 735 is the side of this triangle, and therefore, I will use similar triangles to solve the problem. It looks like a very reasonable thing. We need to find RC, and it makes a lot of sense to get the variable x here because we need to find RC. Well, I will look at my similar triangles, and of course I will use the triangles where these segments are like located. It's very important. For example, I see that this triangle is similar to this one. This side is 735. This is 112 plus x. So let me draw that this angle equals to this angle, and for example, maybe this angle equals to this angle. So I will tell that 735 opposite to this angle, opposite to the same angle will be 112 plus x in the other triangle equals, let's write here PA over BC. Okay, so PA over BC, it's opposite to this angle. It's from the similarity of this triangle and this triangle. Let me also use the fact that this triangle is similar to this one. I will mark that this angle is equal to this angle. This one is equal to this one because of parallel lines. So let me write the ratio. This side of a small triangle divided by the similar side of a big triangle. So 735 divided by 735 plus 112 plus x. And it is equal to, let me use some sides here, maybe it will be the side like, again, PA, opposite to this angle, it will be PA, divided by this side PD. Okay, so as you can see, I wrote just similarity of 2 pairs of triangles, and I have PA here, and immediately, even if I don't know how to what to do next, when I see PA on one expression and on one, it makes a lot of sense to divide these fractions because PA will disappear and maybe we will get something useful from it. So at first, let's simplify this expression. It will look like 735, 847 plus x equals PA over PD. And when we divide this one by this one divided by this one, the result on this side will be simply BC over PD equals this fraction divided by this fraction. Again, 735 disappears, and we will get 112 plus x over 847 plus x. And let's look at this ratio, BC over PD. So BC over PD. Okay, and BC over PD turns out to be the sides of this triangle and this triangle, because these are like similar triangles. And it's amazing because we can tell that right away, for example, that BC over PD, they are like opposite to these vertical angles. It is the ratio that can be expressed like this one, x over 735 plus 112. Because x is opposite to this angle in this triangle, and this side is opposite to the same angle in another triangle. So from the similarity of this triangle and this triangle, BC over PD equals x over this side, which is 847. So this one is x over 847 equals 112 plus x 847 plus x. Amazing, we get a normal equation for x. Let's just make a cross multiplication. We will get 847x plus x squared on the left side, and on the right side we'll get 847 times 112 plus 847x. So now 847x is present on the both sides, right? So it means that this one cancels out, and we turned out that we got the very simple equation that x squared equals 847 times 112. And eventually we need to find x. And of course, the best scenario here, if you try to multiply them, I will just remind you that in AIME competition, the calculator is not allowed. So you should do everything by hand. If you multiply them, after that you will spend a lot of time guessing what the square it is. So it makes a lot of sense to make the decomposition of the right side as a product of prime numbers. In this case, it will be obvious what is the value of x. So let's look at this one. Here, 847, it's obviously divisible by 7. It will be 7 times 121. X squared equals 7 times 121 times. This one is obviously divisible probably by 4. It will be 4 times 28. 4 times 28. Am I correct? Yeah, it will be 80 plus 32. So let's continue here. X squared equals 7 times 11 squared times 2 squared, and 28 is 4 times 7, and this 4 is 2 to the power of 2. So let me zoom a little bit. 2 to the power of 2, so the total power of 2 will be 2 to the power of 4, 7 squared, and 11 squared. It is the value of x squared, and therefore the value of x equals 7 times 11 times 2 squared equals 7 times 11 times 4. And we are left with simple arithmetics. So let me first multiply, for example, this one. It will be 44, and 44 times 7. So 4 times 7 is 28. 40 times 7 is 280, plus 4 times 7 is 28, and the answer is 308. And therefore, the value of x, this side RC, equals 308, and it is a correct answer for this problem. And it is a full solution here. As you can see, it took not a lot of space from us. It's a pretty simple problem, but in order to solve it fast, you need to be reasonable, not to try to write the similarity of these triangles, because I had some students that try to use this similarity in the wrong way. They just write the ratio of all the sides that are present in these triangles, and of course after that they have several big expressions, and it takes a lot of time for them to understand what to do next, because they confuse themselves, because they wrote not only necessary sides that are important for you to solve the problem, they wrote the ratio of all the sides of these triangles, and of course it's like a waste of time. You should be reasonable and to understand if this ratio gives you something or if it gives you nothing. Okay, so let's go to the next problem. Okay, now we will solve number 12. It will be the 5th problem from this paper, and I would definitely choose this one because you have very beautiful configuration on the right side. Equilateral triangle, EFD are midpoints, so EFD is also an equilateral triangle, and after that you draw some line CP, some line AQ, and some line BR, and it turns out that these lines, they intersect in a very interesting manner, that here you have a triangle PQR, and you are asked eventually to find the ratio of areas, area of ABC divided by the area of PQR. You should express it in this form, where C doesn't contain any squares, and after that you need to calculate a squared plus b squared plus c squared, and it will be some integer answer. That's a format of AIME problems. So the problem looks pretty simple. You have a beautiful configuration. Moreover, it looks completely symmetrical from every side. For example, if an observer is located here, if you look from this side, or if you look from this side, or if you look from this side, the problem looks exactly the same. So there is a complete symmetry, and it's very important to understand that when you work on AIME problems, you should use the symmetry right away. It's not a traditional Math Olympiad like US GMO, British Math Olympiad, or any other, where you you have to provide detailed proofs for your assumptions. If you see some symmetry here, you should use it right away. For example, it looks like PQR is equilateral triangle, and should we prove it? In like normal math competition where someone reads your proofs, it's very important to do. But here, no one will read your proofs. The only thing that they care is you have a right answer, and you need to solve as many problems as possible in a very limited amount of time. Therefore, we will use right away the fact that everything looks symmetrical, so we will introduce x as the side of this triangle. We will assume that it is equilateral, and it is a normal thing to do in AMC and AIME. Maybe in terms of logic, it's not the best way to follow, but here the goal is to solve as many problems in a limited amount of time. You need to provide proper answers. No one cares about your logical justification of something. For example, now I work with one student and we solve a lot of advanced AMC problems, usually the problems with last numbers. And you can see here you have also the problem where you have several circles, and circles B and C have the same radiuses. And of course, it looks like this picture has a complete symmetry with respect to this diameter, with respect to this one, and of course this diameter passes through the center of circle A. And if you participate at normal math competition, at regular math competition, of course it's better to justify, to make some proof. But here the only thing that people care is that you provide eventually proper answer, and you need to provide it as fast as possible. Therefore, you immediately draw this one as a diameter and you use it for your own advantage. You don't go into proofs. And here you do the same thing. So here x will be the sides of this equilateral triangle. And in addition, as I told, this picture looks completely symmetrical from every side, and therefore you can also look at this one and this one and this one. It looks like this segment is completely the same as this segment and this one. So it doesn't look like it's directly related to x, so we will introduce one more variable. In general, it's a good idea not to introduce a lot of variables because you will create problems for yourself. But here we will introduce another one, y, because it can't be expressed through x directly. I don't see how we can do it. And also the triangle ABC that we work with, you don't have any value of the side of this triangle. So in this case, we will assume that the side is 2. Why I take the side of 2, not 1? Because EF is a midline and it is a side of this equilateral triangle. If I assume this one to be 1, this one will be 1 over 2 or 0.5, and I don't want to work with fractions. It will be much more convenient to work if this one is 1, which is amazing, and if this one is 1, this is y, it is 1 minus y, and this one will be 1 minus y, and this one will be 1 minus y. As you can see, we noticed the symmetry on this picture, and we use it for our own advantage. And now we will see, will we be able to solve our problem by using this, like maybe some similar triangles. You have several similar triangles here. For example, you can notice pretty quickly that if this one is 60 degrees, then this adjacent angle is 120, and this angle here will be 60 and 60 because it is a equilateral triangle, and this 120, it means that PDB and BPC are similar triangles. And if you write this similarity, it will not give you a lot of useful information. What's better to do is to write similarity of this triangle and this triangle. You see, this line is parallel to this line, and these triangles have a lot of sides that are very useful for us. This CD is 1, and like they have too many sides, too many that are expressed through our variables. Probably we will get some useful information from it. So let's start 1 from the big triangle to the small triangle by 1 minus y equals, so this angle is 60, and therefore this one is also 60, CP over x, so CP is unknown, so probably we will not use this one, equals this one and this one, PD, which is 1 minus y, 1 minus y over y. Okay, so as you can see, let's just check. 1 over 1 minus y equals 1 minus y over y. Great. So there is no even x here, right? So because we didn't know what is the value of CP, and we decided not to use this ratio of sides. And from here, you have an immediate equation that will allow you to find y. Therefore, y equals 1 minus y squared. And if we solve it for y, we'll get the equation that 1 minus 2y plus y squared minus 3y plus 1 equals 0. Discriminant equals 9 minus 4, which is 5. Therefore, y equals 3 plus minus square root of 5 over 2. Very important that y is the portion of the side of length 1, ed equals 1. Therefore, y should be less than 1. If you have here 3 plus square root of 5 over 2, it is obviously larger than 1, so it doesn't work for us. So y should be equal to 3 minus square root of 5 over 2. It is the proper result for y, and here you need to find eventually x, right? Because you are interested at this triangle, and so you can use cosine rule for this triangle. Really, let's redraw it. This side has a length 1 minus 3 minus square root of 5 over 2. We will simplify it very soon, and this one is simply y, is 3 minus square root of 5 over 2. This one is 60 degrees, and you need to find x. So let's simplify this expression. So it will be square root of 5 minus 1. Eventually, this one will turn out to be square root of 5 minus 1 after we add fraction, and the number, let's use cosine rule. So x squared equals square of this one, square root of 5 minus 1 over 2 squared, plus square of this one, 3 minus square root of 5 over 2 squared, minus double product 2 times square root of 5 minus 1 over 2, and then 3 minus square root of 5, 3 minus square root of 5 over 2 times cosine of 60 degrees, which is 1 over 2. So this one and 2 cancels out. Let's work with the other number. So x squared. So the square of this one will be 1 over 4. And let's use 4 as a common denominator. As you can see here, in every expression, 4 becomes the common denominator. So I will not separate 1 over 4. I will just write it like this. So x squared will be on the left side, and every number will be a fraction with denominator 4. So here you have square of this one plus square root of this one, 6 minus 2 square root of 5, plus the square of this one will be 9, 5 plus 14 minus 6 square root of 5, and minus here the common denominator is 4, and I need just to multiply everything here. So 3 square root of 5, 3 square root of 5 minus 5 minus 3 plus square root of 5. So it will look like this. Perfect, and we have one more step to go. Here we can already add 6, 14, it is 20, minus 8 square root of 5, everything is divided by 4. Here we have x squared, and here, before we expand, let's add here. So we have 4 square root of 5, and eventually minus 4 square root of 5 when we expand, and minus 8, but minus in front, so it will be plus 8. Eventually, the right answer will be 28 minus 12 square root of 5 over 4. And the amazing thing here that you can see they are both divisible by 4, so you can divide them separately. And eventually x squared equals 7 minus 3 square root of 5. And it is x squared, right? So eventually you can tell that x equals square root of 7 minus 3 square root of 5. But you don't need x as an answer. Remember that we are looking to find the ratio of area of this triangle to the area of this small triangle. So we need to find the ratio of the area of ABC to the area of PQR. PQR. When you work with this equilateral triangle with side A, the formula for the area is 1/2 the product of these sides times sine of 60 degrees. So it will be A squared times sine of 60 degrees. And if you use this formula for triangle ABC and PQR, on the top and on the bottom, the common thing that you will encounter, 1/2 will be here and here, and sine of 60 will be here and here. So the only thing that is left will be the square of the side of the big triangle divided by the square of the side of the small triangle. So here you will have the side of big triangle AB squared, which is 2 squared, which is 4, and here the square of this side, so x squared. So we will have 7 minus 3 square root of 5. And you need to represent this ratio not in this form, but in the form a plus b square root c. And it's very easy to do. You should multiply on the top and on the bottom times 7 plus 3 square root of 5 to get rid of this this expression on the bottom. So it will be 7 minus 3 square root of 5 and multiplied by 7 plus 3 square root of 5. And here times 7 plus 3 square root of 5. So here 49 minus 9 times 5. 49 minus 49 minus 45, so we will have 4 on the bottom. Here we also have 4 on the top, times 3 plus 3, 7 plus 3 square root of 5. So 4 cancels out, and the total value is 7 plus 3 square root of 5. And it is the ratio of the areas, and we were looking to represent it in the form as a plus b square root of c, where c is a square-free number. Yeah, exactly. So, and we already have this representation, and we need to find the value a squared plus b squared plus c squared, and it will be our final answer, which is 49 a squared plus b squared plus 9 plus 25. Okay, so I would like to add, well, for example, directly. For example, it will be 58 plus 25, it will be 83. And your answer for this problem is 83. So, and it completes our solution. This is it.